So this next example asks us to find all the eigenvalues and the eigenvectors of this matrix A, 3, 8, and 0 and negative 1. So all we need to do is that we just need to find all the vectors V and a constant lambda such that AV equal to lambda V. Remember again that my A, this is the matrix. This is the matrix that they gave us. Right. The V thing, this is a vector. In this case, it's going to be a 2 by 2 vector. And this lambda, this is going to be a constant. It's going to be a scalar. So let me show you just what scalar. So I need to find all the vectors V and scalar lambda so that A times V equal to lambda times V. So let me kind of show you the step here. One thing that we see earlier is that this vector V thing is actually just the same as the identity matrix times V. Because if I multiply the identity matrix by the vector V, the result would be the same thing and the dimension would be the same thing as well. Let me actually kind of just do it on the side here. 1, 0, 0, 1. If I multiply this by V1, V2, we will just get, well, V1, V2, just like I said. So this is the same thing. Okay. So now, my V, this is just the same as the identity matrix. I'm just gonna write I2. Let me actually just write I. So we all knew this is a 2 by 2 identity matrix then, because the size of A, this is the 2 by 2. So my V, this would be just I times V. So my right hand side here would be just lambda times I times V equal to AV. I move the whole thing to the left hand side, so I get AV minus lambda IV equal to 0. So this is similar to what we do in the previous example here. Notice again that this 0 here, this is actually vector. It's actually the 0, 0 vector. Okay. So I have here, this is a matrix. I multiply a matrix by a vector. Minus, I multiply another matrix by a vector. And I get a 0 vector. Well, I can, on the right hand side, I can actually pull out the V. This is going to be the same as V, so this is the distributive law. This is going to be the same as A minus lambda I times V equal to 0. Now, once again, let me kind of remind you. This A here, this is the matrix A that we have earlier. The lambda here, this is what we want to find. The I here, this is the 2 by 2 identity matrix. And the V here, this is the vector that we want to find. The size of this thing, let me kind of put it on the side here. The size, A would be a 2 by 2 matrix. Minus, well actually, if I were to write the numbers down, it would look like this. It would be, let's see, it would be 3, 0, 8 minus 1. So this is my A from here. Minus lambda times I would be 1, 0, 0, 1. Times V. Let me actually kind of move this a little bit. I run out of space. Okay. So that would be this guy, whole thing in the parentheses, times V, V1, V2. Equal to the 0 vector 0, 0. Okay. So this is the equations that we want to solve. This is the equations that we want to solve for lambda and V. If you were to write this guy down in numeric, this is what you're going to be looking at. Let me actually use the same color. Okay. So, what do we do from here? Well, in case you don't remember, I'm actually going to have to ask you to go back and look at lecture 8 in case you do not remember. But we see from back then that whenever this guy has a solution, there's one thing that needs to happen. The thing that needs to happen is that when I have a matrix And when I multiply a matrix by a vector v, which is not a zero vector, my eigen vector, I don't want this to be a zero vector. If this thing has a solution, what needs to happen is that I'm gonna need the determinant of this guy has to be 0. So, to solve for lambda, I'm gonna need to have the determinant of the, let's see, a minus lambda I to equal to 0. So now, I can focus on solving for lambda here because I already knew a and I already knew I. So, what are these guys? I'm gonna need the determinant of, let's see, my matrix A. Well, I actually kind of write it back here. That would be 3, 8, 0, negative 1, minus lambda times 1, 0, 0, 1. I want the determinant of this guy to be equal to 0. So that means I want the determinant of, well, if I multiply the lambda inside the matrix, this is what I'm gonna get. So I multiply lambda, so this is what I'm gonna get. It seems like again I've just erased the whole thing. So that would be 3 minus lambda, 8 minus 0, and then 0 minus 0, and then negative 1 minus lambda. Voila. So I'm gonna want the determinant of this guy to equal to 0. But what is the determinant of this guy, the determinant of this matrix? That would be just, if I multiply the 3 minus lambda times minus 1 minus lambda minus 0 times 8 equal to 0. So I just want this whole thing to equal to 0. So I want 3 minus lambda times negative 1 minus lambda to equal to 0. And that can only means that my lambda can only take 2 values. Lambda has to equal to 3, or my lambda has to equal to a negative 1. So these two guys, they are the eigen value for the matrix A. Lambda equal to 3, and lambda is equal to a negative 1. So now, I have the two eigenvalues. Now I just need to find the eigenvectors that correspond to each of the eigenvalues that I have just found. So, what do I do next? Remember again, the equation that I need to solve is that I need to find a minus lambda I times v equal to 0. Now I already have the lambda. Lambda can only be one of the two values, 3 or negative 1. So I need to do this in two cases, when lambda is equal to 3 and when lambda is equal to negative 1. In each of the cases, I have to write down a minus lambda, and I need to solve for v such that a minus lambda I times v equal to 0. So this is I, by the way. So a minus lambda I times v has to equal to 0. Okay. So what is a minus lambda I then? Well, if lambda is equal to 3, remember again that my a would be 3, 8, 0, negative 1. So my a minus lambda I, this would just be, let me see, this would just be 3 minus 3, and then 8, and then 0, and then negative 1 minus 3. Notice how this thing is actually just the same as the final matrix that we have seen earlier, except that I knew already that my lambda is equal to 3. Or you can actually also see this as the matrix A, which is 3, 0, 8, negative 1, minus 3 times the identity matrix. So this would just be the same thing. You can do it from here and you can do it from here. Voila, okay. Actually, okay, that's fine. So, my matrix A is 0, 8, 0, negative 4. I do the reduced row echelon, that would be just 0, 1, 0, 0. So I knew then the the null space for this matrix would be just the span of the vector 1, 0. So that means I have found my first eigenvalue, which is 3, and the what did I say, eigenvector? I mean eigenvalue. I have found my first eigenvalue, lambda equal to 3, and the eigenvector corresponding to 3 would be just anything in the span of 1, 0. Now then, if you want to check whether this is true, I can check as well. So I'm just gonna multiply 8, 3, 8, 1, negative 1 by this vector here, 1, 0, and let's see what I'm gonna get. I'm gonna get 3, and I'm gonna get 0. And look at how this is, look at how 3, 0. This is just 3 times 1, 0, which is the original vector that we have. So I have now A here times V, which is eigenvector, equal to 3, my eigenvalue, times 1, 0, which is my eigenvector. So now let me do this again for lambda equal to negative 1. So let me actually just write the my matrix already. My A minus lambda I would be just A plus I, because my lambda is negative 1. A plus I would just be 4, 8, 0, 0. The reduced row echelon form for this guy, so I'm just gonna speed up a bit, is this thing. And the eigen vector corresponding to this guy would just be the span, anything in the span of negative 2 and 1. If I were to check the answer, I'm gonna have 3, 8, and then 0 and negative 1 times negative 2 and 1. This would be 3 times negative 2 plus 8, so that would be, let's see, that would be 2, and then I will have 0 minus 1. Again, we have this guy, it's just negative 1 times negative 2 and 1. So, I have here A times V equal to negative 1, my eigenvalue from here, times V. So then, all my eigenvalues are 3 and 1, and the eigenvectors corresponding to 3 are anything in the span of 1, 0, and the eigenvector corresponding to negative 1 are just anything in the span of negative 2 and 1 here.